So let me continue the discussion for the calculation for the magnetic field. 到目前为止的话，你应该是觉得这个计算 magnetic field 的时候呢 ，it's not for the direction it's not so straightforward, all right? Because you are doing calculation for curl of B through the Ampere's law, and this curl operator, you always have to sort of remember your right-hand rule. And this B is definitely not parallel to J. And this makes your calculation sort of tedious and a little bit complicated when you try to determine the directions for B and J. Okay, so let's think about a way to fix this problem. And from the first postulate of the magnetic field, you have divergence of B equal to 0. But from the vector, one of the null identities, you can define B equal to divergence of some vector. Because curl of some vector, because divergence of curl of some vector is always equal to 0. Okay, this is one of the null identities I provided you when we talk about the vector calculus. Okay, so let's define B to be some curl of some vector. And this vector is not yet well defined because we haven't defined the divergence of this vector yet. 在电磁学里头，我们上回讲过，就是你如果说要定义一个 vector 的话呢 ，you have to define curl of it and divergence of it. And then if you give the same boundary conditions, this vector is going to be unique. Okay? And this is called Helmholtz theorem, right? So let's define this B to be the curl of some vector and then put into this Ampere's law and see what happens. Okay, so you have double curl of some vector, and on the right hand side still you have J multiplied with the current density. And if you still remember the definition of the vector Laplacian, then you can decompose this into two terms. The first term is gradient of divergence of A minus this vector Laplacian. And then on the right hand side you have mu naught J. Okay. If you go back to the chapter 3, you can write down this expression based on the definition of the vector Laplacian. Okay. Now, you define B to be curl of A. But as I say, we haven't defined yet the divergence of A. So it's our liberty to, you have the freedom to define divergence of A. So let's just define this divergence of A equal to 0. For now, okay, 在目前我们先把它定义成 divergence of A equal to 0. Okay, 然后呢，在这种状况之下 you can reduce this expression to vector Laplacian A equal to minus mu naught J. Okay, the good thing about this is that this A is parallel to J. 它在同一个方向上头，所以我们在计算的时候呢 we don't have to use our right-hand rule anymore. And the calculation is more straightforward because A is proportional to J. And once you solve A from this expression, you can come back to calculate your B according to this. Okay, and this A is called vector potential. Because if you can compare this expression with Laplacian of V, this is a scalar equal to minus rho divided by epsilon 0. This is this V is called scalar potential. This A is called vector potential. Okay, if you know how to solve this, you know how to solve this, right? Because in the XYZ coordinate system, you have Laplacian A x equal to minus mu naught J x. And this can be y, this can be z, this can be y, this can be z. So you know the solution from this. The solution of this is equal to 4 pi epsilon naught 1 over this, and then you have rho dv prime over r. 还记得这个 vector 这个 scalar potential， 你如果有一个rho distribution, the charge distribution in space, and then you try to figure out V at a certain location R, then you do this integration to get your scalar electric potential at the distance R away from your source, right? So if you compare these two expressions, then for example, you want to calculate A of x, the x component of the vector potential. Then you have epsilon here downstairs, and you have mu 0 upstairs. So you just move this up. You still have 4 pi, and just move this mu naught up to the numerator. And then you do the same integration. You have Jx component of the current density over R, and then integrate over the volume of your source. Right? 你如果会写这个的话，这个就写得出来。那if you want to do y direction, you just choose y direction. If you want to do z direction, then you choose z direction. So finally, you end up having a solution for the vector potential equal to 4 pi mu naught, and then your volume integration for the current density, and this R is the distance from your source to the location of your interest. OK， 所以很轻易的一个置换，从这个 scalar potential 到vector potential， 这个解就写出来了。Any question? 这个，一个这个 vector， 在你没有定义它的这个 divergence 跟 curl 之前的话，它的解有很多解。那所以呢，你定义了它的 curl 之后，你还可以定义它的这个 divergence， 由你选择。它的解才是一个唯一解。那所以呢，你那里算出来的结果呢，也必须符合 divergence of A 等于0的这个条件。OK， 这个条件必须吻合，你会有个唯一的解。那在随时间变化的场里头呢，你也要定义这个 divergence of A， 它的这个样子呢，会是定义成 divergence of A 会等于负的这个 time derivative of electric potential with respect to time. OK， 在随时变场的时候呢，你还是要定义这个 divergence of A， 但是这是其中一种定义法。那在量子力学里头呢，即使随时变的场它也是定义成这个样子。这个叫做 Lorentz gauge， 这叫 Coulomb gauge。他们有他们的名称在那个地方，但是呢，你一定要定义出它的 divergence of A 出来，你解出来的 A 才是一个唯一解。OK， 那不同的这个物理问题里头，你可以选择你对这个 A 的 divergence of D 的这个 divergence of A 的这个定义。那 in this textbook, when we talk about time varying field, we choose this definition, and this is called the Lorentz gauge. Okay, so later on, when we talk about time varying field, we're going to adopt this definition for divergence of A. At this moment, we don't talk about time varying field, so we simply pick up this definition. OK， 因为在这种 definition 状况之下呢，你的 G 的这个你的这个 A 很容易就解出来了，方便而已。OK， once you solve the A, then you come back to do this curl of A to get your B, and so this is more like a mathematical tool. 它是一个数学的工具。A mathematical tool allow you to calculate a field that is parallel to the direction of your current. Therefore, you don't confuse yourself with the directions of B and J. OK， 所以呢，在这里呢，你会问说 ，if there's any physical meaning of A, OK, if you insist to get some physical meaning for A, then we can do this calculation. Well, if you do a surface integration of B, then you get magnetic flux. Now that we define B to be curl of A, so you can reduce this to a cross-path integration by using the Stokes theorem. So you end up having the circulation of A equal to the magnetic flux. So if you want to calculate the magnetic flux over some area, in fact, you can just do a circulation integration for A bounding this area to get the total magnetic flux. Okay, so in some sense, the circulation of magnetic vector potential equals the magnetic flux passing through the surface in the circulation path. So you can think about this as a sort of physical meaning for A. OK， 但是在计算上头的话呢，这个 A 因为这个 A 的方向跟你电流方向一模一样，所以在计算上头变得相对简单很多。OK， so let me give you one example. 这些我们都看过。Let me give you one example. Well, suppose that you have a small piece of current ended here and start here and ended here. And you want to figure out the magnetic field at this location. Well, you cannot use Ampere's law to do this calculation because the termination of the wire breaks the symmetry. So the magnetic field here and here, even given the same R, but if you choose the location here, the magnetic field here is going to be different from the magnetic field here because the termination of the current. Okay, so we have to sort of do the integration of the current piece by piece from this location to this location. So let's assume that if you want to calculate the magnetic field directly, it's going to be quite difficult. Okay, but now that you have definition of A is parallel to the current, so you can just do just pick up this integration and specify your direction along z direction, because you only have the current along z direction. So what you need to do is do simple integration. Az equal to 4 pi, this is mu naught, and then you have J around z direction, and integrate over the source and divided by R. Okay, 但是在这里呢，这个 volume, you have a uniform cross section for the wire. This dV prime is at the source, and you have a uniform cross section for the wire. So basically, you only have to calculate around the z direction, integrate around the z direction, because this gives you the small volume. Okay, and this Jz multiplied with this S, Jz multiplied with S gives you the current inside this wire. So what you need to do basically is V naught 4 pi R integration. This is the dz prime, and the whole thing is around z direction. OK， 那在这里呢，我们可以把原来那个式子做一个这么一个整理。OK， this is the equation we have from this previous the expression I wrote on the board. But this dV can be decomposed into the surface, the multiplication of the surface along some direction along the current direction. So you can convert this expression for A into this equation and pull out the current outside. If you have a uniform current through a wire, OK， 所以呢，你会得到这么一个式子。这个式子呢，这个 A in general along any possible direction, you have mu naught I divided by 4 pi, and then this is path integration for your source. OK， 那通常这个电流是在一个 wire 里头 ，usually is a cross loop. So very often that you put a symbol for the cross loop for this integration. Okay, and don't forget this is the vector along the direction of the current float, and this R is the distance between your source to the location of your interest. So suppose that you have a wire like this, and the coordinate of this wire is defined in the primed coordinate system. And then suppose you are calculating a vector potential somewhere in space contributed by, say, this point of current, all right, dl prime. Then the R, the distance R, is going to be from this point to this point. This is your R. But your origin, 你的这个坐标系 the origin could be here, okay? But this R is the location from your source to the point of your interest. 好，我们来看一下这个例子怎么算。OK， 在这个例子里头 ，we have to figure out a few things. So suppose we want to find the magnetic field right at the center between these two lines, but at a distance r from this wire. So right here, I want to find the magnetic field. So I need to find out. This is from here to here is R, and this is a piece of current. Okay, a piece of current having a current in this direction. And let's just pick up a small section of current at this point. From here to here, we call it Z prime. Okay. And the distance from here to here, we have an expression of R. right? So clearly this r is going to be equal to square root of r squared plus z prime squared. 没有问题 right? Because this r is defined to be the distance between your current element to the location of your interest. 没有问题 right? 在这个式子里头，你如果看右边这个式子的话呢，你还得知道这个 dl 是什么东西 dl prime。这个 dl prime 呢，没问题，是叫做是这一小段，所以这是 dz prime along z direction. Okay, now you are ready to calculate a. This a is going to be along z direction. That is equal to I mu naught I divided by 4 pi, and then cross path integration means that you have to integrate for z prime from, say, minus L to L, minus L to L, and then your R, you already have the expression for your R, so you put it downstairs. That is R squared plus z prime squared, and upstairs you have a dz prime, az. So you are calculating something, a vector that is along the direction of the current. So conceptually, it's much easier because you are calculating a vector that along the same direction of the current. You don't need to use the right-hand rule anymore. So once you do this calculation, then you'll be calculating B from curl of A. And this operation can be found from a table. 你如果把这个 a 算出来之后 curl operation 的话呢，是有公式可以带的，所以在计算上头呢就简单的多了。Okay, so you figure out the r to be this direction and do an integration throughout the source between minus L and L, then you end up having this expression. And then once you have this expression, do a curl of A to get B. So you end up having this expression along phi direction for your magnetic field. 那 phi 的方向呢，跟着电流方向是互相垂直的 ，alright。但是呢，在这计算过程里头，你可以先算一个这个物理量是跟这个电流方向一样的，这就简单多了。Alright, any question? Good. 但是有些人如果是坚持你要用这个 B field 下去算，也是可以的。我们可以是直接在这上头做一个 curl operation。OK， 然后呢，这个数学上头是可以算得出来的。If you do a curl operation to this integration, then you'll be calculating the magnetic field at this point. 在这个地方的坐标，它的定义不是 prime coordinate system， 是一般的这个 unprimed coordinate system. So you have to do this operation. OK， 那这个的微分其实是不存在，因为你是对这个 unprimed coordinate system 做一个微分的动作。OK， 所以基本上你是要对 R 做一个这个 curl 的这个微分，然后呢方向呢取这个方向。OK， so first pick up this vector identity. If you do curl of a variable multiplied with a vector, then you can do differentiation by parts. Okay, first do a differentiation with respect to f, take gradient of this, and then do a cross product with g. And then you have a second term, you leave this f outside this operator, and then multiply f with this curl of g. 所以这是这个 vector calculus 里头的一个公式 ，OK， so let's do it。在这里呢，你的 g 是 dl prime 这个 vector， 你的 f 呢是 1 over r，OK， 所以呢， 你可以做一个这个一步一步算一下，免得一下子你搞糊涂了。Okay, so we can do a gradient of 1 over r cross product with dl prime as the first term, and then you can do a second term, that is 1 over r is outside the operator, and then you do a curl of dl prime. Okay, but this differentiation is taken at the unprimed coordinate system, and this prime coordinate system is with the source. 这是2个不同的坐标系统，所以呢，这个 differentiation 呢，基本上给你0。So you only have to do this. Okay. 那这个呢 ，r 呢是定义在 unprimed coordinate system， 所以这个 gradient of 1 over r is equal to minus 1 r square er along r direction. Okay, so once you have this, you can decompose this into this expression into this expression. Okay, and this is called Biot-Savart Law. And this equation allows you to derive the expression for B field through this kind of distributed integration. 只是呢，方向你必须要抓得很好。Okay, and this is r square comes from this r square, and this ar. Previously, you have AR crossed with DL prime, but to remove this minus sign, we reverse the order. So you have DL prime crossed with AR. Okay, you reverse the order. 那这个呢是所谓的 Biot-Savart Law. So we can go back to the same question, the same problem, and use Biot-Savart Law to solve it. 所以在这个问题里头呢，我们再重新做一次。我们要知道的是什么 ？R remains the same if you want to calculate the magnetic field at this location. R remains the same. We need to know what dl prime. Still the same. We have dz prime along z direction. We need to know AR. AR is equal to what? R divided by R. 这个 R 呢，这个 R 是等于 R AR 减掉 Z prime AZ。不，这个是呀，没错，这个 vector 减掉这个 vector 得到这个 vector。Right, so you can write out AR and divided by R. R is like this. 所以呢，这里你可以直接把它带进来 ，square root of R square plus Z prime square. And then you have to do a calculation dl prime cross with AR. 那这里有 AZ cross with AZ， 所以这个 AZ cross with AZ is going to give you 0. So you don't have to worry about this term. Okay, but you do have to worry about this term. You have R AZ cross with AR. 这个是什么？这是 A phi， 没有问题 ，right？AZ cross with AR give you A phi. So this gives you R dz prime A phi. Now, you have everything you need. This one and this one, and put it into this expression. Put it into Biot-Savart Law.这个地方我写很多的黑板，就是不希望就是我在讲这些式子的时候呢，你觉得我讲得太快 ，OK？ So you B, now you use Biot-Savart Law, so just copy down the prefactor, and then you do a path integration again from minus L to L, and upstairs you have dl prime cross with AR, and we have the R d z prime along A phi direction. And downstairs you have R square. R square is R square plus Z prime square. So you have to do this integration. And the direction was determined to be along phi direction. OK， 没问题。在这里头呢，你就是得把这个个别项呢，把它给算出来，然后做一些这个 vector 的 cross product。OK， and then you end up having the expression, the same as before. OK， 就是跟之前你在这里计算出来的结果一样。Along phi direction, you have the magnetic field at this point. 没问题 ，right？ 所以这些都是这个解题的技巧，但是呢，most people is going to find that this integration is a lot easier because A direction of A is along the same direction of L, the same direction of the current. 所以呢，你要用什么方法解，你可以自己选。那找一个你觉得最简单的方式来解它。OK. Any question? « 没问题 ，right？ 好，下一个问题呢是有一点变形。之前的话只有一个小的这个电流，一段小电流，但是你知道。这电流不会突然出现，突然消失。So usually you have a current loop like this. Okay, a current usually is going to form a loop. If the question is to ask you to figure out the magnetic field right at this point, well, you can get the answer right away. 因为基本上这里的这个 magnetic field 只是这一段电流每一段电流的贡献加到这里来，所以呢，用一下你的这个右手，你会发现 well, you only have to multiply this answer with a factor 4, but in this coordinate system, this direction is defined to be z direction. Okay, so this is a very quick answer for this problem. Just multiply your previous answer with a factor 4, and then put the direction along z direction. And previously we have minus L to L right here. And for this problem, the total length is W, so you have to convert it. This W is equal to 2L. Okay, so just convert the variables, you get your answer. 有问题 ？OK， 这个方形的东西好算，圆形的东西也可以算。Okay, if the question is to ask you to figure out the magnetic field somewhere here, 对这些问题来讲的话呢，你都找不到一个这个 constant B field 的一个 loop 一条线，所以呢 you cannot use Ampere's law to calculate it. And just like when you do the electrostatics problem, if you cannot find the Gaussian surface, then you have to do distributed integration. OK， 那在这个这个磁场的问题里头呢 ，the distributed integration is to find just do an integration around the path of the current. Right， 所以呢就是这个 Biot-Savart Law 或者是刚刚算出来这个 vector potential 的这个计算。OK， 所以在这个问题里头，你要算这里的 magnetic field subject to a current loop like this. Well, same thing, you basically you have to figure out a few variables. Okay, this is dl prime cross with AR, and then this is R square. So if you want to use this for your calculation, then you need to figure out what dl prime is. Then you need to figure out AR. You want to figure out R. OK， 那在这里呢，你的 dl prime 是这个上头一小段的电流。In this coordinate system, this is B d phi prime. This prime is associated with the source coordinate, and this is along phi direction, right? And this R is the distance from your source to the location of your interest. 所以呢，这个三角形，你这个 R 会是等于 z square plus b square 开根号。Okay, and then now you have to figure out what R is. R is a vector here minus a vector here. So this R direction, R divided by R is equal to, you have to write the expression for this vector. This is equal to Z along Z direction minus B along R direction. Right, this vector is B along small r direction. This is Z along AZ direction. So once you have these three elements, you can put it into this expression and do a cross-path integration to get the answer. OK， 所以呢，在这里你 R 在这个地方找出来的 dl prime， 你也找出来的 b d phi along phi direction. R is this value, right? And then you do a cross product dl with AR. OK， 那这时候呢，你就可以做一个这个积分的计算。所以呢，每一步都有告诉你。OK， 有没有问题？在这个例子里头，你如果用那个A 方 A 下去算的话呢，这个就不太容易了，因为在这一点上头，你的 A phi 是这个 phi 的方向 ，OK， 但是是在一点上头，这个很难算，所以呢，你直接用 B 的方法开始算。最后一点时间，我们助教帮我们准备了一点这个实验给大家看。这个是我昨天到深坑去吃臭豆腐的时候呢，帮我小朋友买了一个弹簧，蛮好玩的。So I figured that perhaps I can use this to make a solenoid for you. So I borrowed this from my daughter for 1 day only. OK， 他们非常这个 very reluctantly to give it to me for 1 day. So hope that I don't think I'm going to burn it anyway. 所以呢，我们看看能不能做一个 solenoid 出来，其实蛮好玩的。哇 ，oscillation。所以呢，我们看看这是助教有没有什么我们看看能不能看到这个 magnetic field。 Well, I told you that it's a major accomplishment in science when you connect the current to a magnetic field. So I'm going to send current into this piece of wire, and hopefully I can produce some magnetic field. So somehow I need to have a way to pull out this. And then we have batteries. 看看我们能不能今天产生磁场出来。有一个大电流，哦，你那里已经有了。然后呢，我们如何把这个张开？把它拉烂的话，它已经会张开，但是我女儿会哭。OK， 但是你加电流的时候，它会产生高热，你的手没办法去抓它。啊。可不可以夹住？对，但是somehow我们要把它撑开，来，撑开的方法是。撑开的方法是，对，你就一端把它夹住，哦，另外一端把它拉开来，但是，然后呢，这材料是铁的，金属材料我不是那么确定，我想这个大概是铁，它才有这个弹性，然后呢，我们还需要。一个最好有个指南针，我们助教帮我们绑了一个这个 ，OK， 这是一个回纹针，是铁做的。我们看看通电之后呢，你已经通了吗？你要 touch 它，然后呢，看这指南针会不会被吸过去，好不好？当然。并不是所有的实验都会成功。哎，好像真有那么一回事。然后 ，OK， 助教，停下来。OK， 我不要呼吸。没动静。我们。来，我放到正中央，看看它会不会。你们当研究生的时候就要做实验 ，right？ 然后呢，等到你看到第一个实验数据的时候，就是快毕业的时候。所以我们3分钟之内要做一个成功的实验，没那么容易。我开始在帮自己找借口。我有一个比较小的那个回纹针 ，OK。你这样子的话，后面同学看不到。我们有一个比较小的回纹针 ，right？ I drop it。哇，这个又太重了，大概没办法。来，我们看看这个 solenoid， 在这个。不晓得是我手在动，还是它翅膀在吸它。不过你知道看到它在动。So hard to determine, right? 我都放到这里头来呢。Okay. I think this magnetic field is too weak. 我们需要有一个指南针。你们身上有没有任何指南针 ？No. Okay. The good thing about this internet era is that I can always pull out something from internet to show you the experiments. So I think the current is not strong enough. But I do have one film that I can share with you. Okay, there's one film in the YouTube, and it's a successful experiment, so you can really see it. So let's look at the film.
Charges, that is a current, create magnetic fields. Here I have a coil of wire with a compass in the middle, and the two ends of the coil are attached to a battery, or rather will be when I connect up this other clip. Notice the compass needle aligns with the axis of the coil when the current is flowing.
OK， 所以我们这个实验是成功的。去年的时候，我们是用我们实验室里头一个 coil， 然后呢，一个小的这个量磁场的一个小的这个 magnet bar， 然后做给同学们看。然后昨天去跟这个我们实验室的几个同学去深坑吃臭豆腐的时候，沿路我的小朋友想这个吵着要买这个，我想大概可以做一个实验给各位看，所以很抱歉没有成功，我们要加一个大电流才会成功。Anyway， any question？ 有没有任何的问题？我再回去玩一玩，看看能不能看到什么东西，再拿给你看。有可能电阻太大，但是通常一个金属的话，它的电阻应该不至于太大，我觉得是因为这个的大概重量大了一点或怎么样，就是它吸不动。那你如果是指南针的话呢，它就相当的敏感，相当灵敏，因为去年的话我们也是用 battery， 然后呢类似这种 coil， 然后里头就是一个磁铁大概这么大，放到里头去，它会转动它的方向。OK，Anyway， 我再玩一玩，玩出什么心得来再给各位看。有没有问题？没有问题的话呢，我们今天上课到这里，然后呢，下礼拜一我们要考试，下礼拜三我们会介绍这个 magnetic dipole， 好不好 ？OK。